If you want to master your NMR problem solving skills, then you are in the right place. Welcome to the NMR Challenge series, where each video presents a new NMR spectroscopy problem from beginner to advanced level. Here, we systematically analyze 1H and 13C NMR, along with 2D techniques such as COSY, NOSY, HSQC, and HMPC, depending upon the problem, to uncover organic structures step by step. So let's get started.
We have taken this NMR challenge from Pavia Spectroscopy book, 4th edition. Page number is 222. Problem is 11. We have to determine the structure of the organic compound having molecular formula C9H8O1 from the given spectral data such as IR values, 13C NMR data, and 1H NMR. By the end of this video, you will understand how to calculate the index of hydrogen deficiency, how to interpret 1H and 13C spectra, how to analyze advanced spectra such as DEPT 90 and DEPT 135, and how to integrate all the data logically to identify the correct structure of the organic compound. I follow a specific step-by-step process for determining the structure of organic compound, and I would like to recommend you to follow the same approach. First, look the IR value or IR spectra to determine the functional group present in the molecule. Then calculate the index of hydrogen deficiency, which gives you information about number of pi bonds or rings, or it could be both, present in the molecule. According to my experience, if index of hydrogen deficiency equal to 5 or more than 5, then we can say that this compound contains one benzene ring. Then look at the 13C NMR. Normal 13C NMR gives signal for all sorts of carbon, means all types of carbon signals you will see. Then look at the 90 DEPT 90 NMR, which gives you how many types of CH methane carbons are present in the molecule. After that, look DEPT 135. In DEPT 135, only those carbons showing the signals which possess the hydrogens. So it means the signals for quaternary carbon or carbonyl carbon will be absent. Therefore, you can easily conclude that which signals belongs to the quaternary carbon by comparing with the normal 13C carbon spectra. And remember that methane CH or methyl CH3 peaks coming in the positive phase, means in the upward direction. Methylene signals comes in the negative phase, it means in the downward direction. And at the end, look 1H NMR. The number of signals in the 1H NMR is equal to how many types of protons are present. If you are seeing that number of hydrogen signals are half of the total number of protons present in the molecules, then it means your molecule have symmetry. And same in the carbon NMR also. If you see the carbon signals, let's say 5 carbon signals and there are 10 carbons, it means the molecule has symmetry. Okay, the splitting patterns in 1H NMR following n+1 rule, then you can get the information about the neighboring protons, and eventually you will understand which type of functional group or group present in the molecule. Substitution patterns in case of benzene ring you can determine by the splitting pattern. Chemical shift values is very important to remember because it will gives you information about the shielding or deshielding of the protons. For example, I would like to recommend you to remember few chemical shift values. For example, if alpha hydrogen is connected to the ketone or ester, then it is coming in between 2 to 3 ppm. If the carbon is connected to the electronegative atom such as oxygen, nitrogen or fluorine, then the signal will come around 3 to 4.5 ppm. If it is connected to the bromo or chloro, then it comes between 2 to 3 ppm. The signals for alcohols or amines is variable, so you can see from like aliphatic regions up to the 5 ppm. Phenol signals usually comes around 5 ppm. Now look at the alkenes, which comes from 5 to 7 ppm. For aromatic compounds, the signals comes from 6.5 ppm to 8.5 ppm. Aldehydes protons gives characteristic signals between 9 to 10 ppm, and similarly carboxylic acid signals will come from 11 to 12 ppm, always beyond the 10 ppm. Okay, if you remember these values, then you can easily figure out the presence of the functional group in your molecule. Okay, so let's solve this problem step by step. So first look at the IR value. So IR value is 1746 per centimeter. So this indicates that the compound may have ketone or aldehyde group. But if you see the 1H NMR, there is no aldehyde proton. It means the compound have ketone group. Now let's calculate the index of hydrogen deficiency. So 2C plus 2 plus number of nitrogen minus number of hydrogen minus halogens divided by 2. So the value will be 2 multiplied by 9 plus 2 plus 0 minus 8 hydrogen 0 halogen divided by 2. So it will be, so the degree of unsaturation is 6. This means that the compound have one benzene ring which contribute for the 4 degree of unsaturation. So how many left? 2 degree of unsaturation left. So 1 degree of unsaturation you can assign to the keto group, as we can see from the higher data. So now 4 plus 1 plus 1. So 1 degree of unsaturation is left. Now let's look at the carbon NMR. From the carbon NMR, normal 13C NMR, there are 5 signals. So let's draw this carbon NMR. So one signal is at 44 ppm, another is 125 ppm, then 127 ppm, 138 ppm, and last one is 215 ppm. This signal 215 ppm clearly indicates the presence of carbonyl group of ketone or aldehyde. We have already ruled out the presence of aldehyde because there is no proton in the 1H NMR. So we can clearly say that the compound has keto group. Okay, now look at these 3 signals. These 3 signals belongs to the benzene ring, right? But the compound has 9 carbons. 9 carbons, right? And how many you are seeing? 1, 2, 3, 4, 5. You are seeing only 5 carbons. It means the compound has plane of symmetry. Okay, the compound has plane of symmetry. Now carefully look at here. There are 3 benzene carbon signals, and benzene must show the 6 carbons, right? So under what condition it is going to show the 3 signals? So let's say if the benzene is monosubstituted, then it will show how many signals? 1, 2, 3. It will show the 4 signal. If the benzene is disubstituted, and which type of disubstituted? This type of 1, 2 disubstituted benzene ring will show you 1, 2, 3 signals, right? If you have para substituted benzene ring, then it is going to show you this 1, 2. If it is X, this is also X group. So it means the benzene ring is 1, 2 disubstituted, and both are same. Here and here the group are same. Okay, now look at the depth 90 NMR. In the depth 90 NMR, there is no signal for 44 ppm. It means this signal at 44 is either belongs to the methyl or CH2. If you look at the depth 135, in depth 135 it is showing in the negative direction, in the negative phase. So it means this signal is belongs to the CH2 group. So 44 ppm signal is belongs to the CH2 group, and 125 it is showing the positive. Okay, so it means 125 it belongs to CH of the benzene, and 127 is also positive. This is also CH of the benzene, and 138 is not showing any signal, and 215 of course this is belongs to the keto, so no signals. It means 138, this signal is quaternary carbon of the benzene ring. What does it mean? It means benzene is has substitution, and that substituted carbon is coming at 138 ppm. Now look at the in the depth 135, this is positive, this is positive, and there is no peak in this depth, and in this one also no peak. So the compound has only 2 types of CH of benzene ring. It means benzene is, some substitution are there on the benzene ring which making it symmetrical. Okay, so there are 3 signals in the aromatic region from the benzene ring. So as we have already concluded that the benzene ring is 1,2 disubstituted, and this 1,2 disubstitution is symmetrical. It means the, let's say if this is the X group, then here is also X group, and this is the plane of symmetry. So 1, 2, 3, right? Now let's look at the 1H NMR. In 1H NMR, we are seeing the 2 signals. It means there is only 2 types of the protons. This further confirms that the molecule has plane of symmetry. And the first signal is around 3.5 ppm, which is singlet, and the integration value is 4 hydrogens. So this means that there is no neighboring hydrogen, or it could be equivalent or identical. This also indicates that there could be CH2, and we have already seen in the carbon NMR that this 44 ppm signal at 44 ppm is belongs to the CH2, and this could be probably attached to the oxygen because it is going in the deshielded region, right? Okay, now we have another signal around 7.2 ppm, which belongs to the, for sure belongs to the benzene proton, and this is also a broad signal and belongs to the 4 hydrogens. So this further confirm that our benzene ring is disubstituted. We have already confirmed this from the carbon NMR. Now further confirmation comes from the proton NMR that it is disubstituted. Now, as I told you, the disubstitution is 1,2, right? 1,2 disubstitution, and the compound has CH2 and keto group. Remember that we have 4 degree of unsaturation from this and 1 degree of unsaturation from this. So 1 degree of unsaturation is left.
Okay, now we have all pieces of information. It is time to put them together. This step requires careful logical thinking, and we must consider all the possible structures and identify the one that is fully consistent with the molecular formula, index of hydrogen deficiency, and all the spectral data. So let's do it together.
We can write the structure like this. Let's say there is a CH2, right? This one, and then CH2, and then oxygen, keto group, and then connect to the benzene ring. So this is known as 1-indenone. Do you think this is the correct structure? Look at this. This one will show CH2 and CH2, two types of CH2, but the compound have only one CH2, right? 44 ppm. And another thing, this CH2 and CH2 should be equivalent. So therefore, this cannot be the correct structure. Let's try to modify this structure a bit so that the molecule can have plane of symmetry. So we can write the molecule like this, which is 2-indenone. Now look at this. This CH2 and this CH2 is identical, which is coming at 44 ppm. This is coming at 215 ppm in carbon NMR. And now look at this 1, 2, 3. 3 types of the carbon, right? And how many quaternary carbon were there? There were only 138 ppm. So this one belongs to the 138 ppm. Okay, and in the 1H NMR, we should have this one doublet, this one doublet. So there should be 2 doublets. But what we are seeing, only one signal. This means that these hydrogens are very close in chemical shift value. Therefore, you are seeing the one single peak. Okay, so the correct structure for the given problem is 2-indenone. Okay, so this is consistent with the carbon NMR. Now let's look at the let's try to match with the proton NMR. So in the proton NMR, you should have this signal is belongs to the CH2, 4 hydrogens, right? This is, and this 4 going to the same as I told you that chemical shifts value are very close. That's why you are not seeing doublet of doublet. Otherwise, you must see like this doublet of doublet. But due to the same almost same chemical shift value, they are merging, and you are seeing like a broad signal for as a singlet. And chemical formula. So how many carbons are there? 6, 7, 8, 9. How many hydrogens are there? 4, 5, 6, 7, 8. 8 hydrogen, 1 oxygen. Okay, so it is consistent with the molecular formula 1H NMR and 13C NMR. Therefore, the correct structure is 2-indenone.
So that's all for today. I hope this video helped to strengthen your NMR skills. Keep practicing because mastery comes with consistency. And I will see you in the next video with the another exciting NMR challenge. Make sure to subscribe so you don't miss it. Till then, take care. Bye bye.